Welcome to another Great Cow BASIC tutorial. This is part 10 for the PIC18FxxQ41 chip family, and today we're going to be looking at something that I get pretty excited about. Okay, it's so simple, but it's pretty exciting. Great, let's get into the deck of slides. Let me get set up properly. There we go. So we're going to do CCP stroke Pulse Width Modulation. So we're going to use the CCP module to generate pulse width modulation to dim the LEDs that we've been looking at on this PCB. So what I've been using is a microchip, a low pin count demo board. I'm still waiting for my Curiosity Nano board to come in. And let's have a look at that in the lab, because it's always good to have a look at it in the lab. Oh, look, there's more kit in there today, look. So, but this is the board down here, the green thing, and I've got some other stuff connected, which we'll come into later on. So the layout looks like this, and I'm put this in every time because you can reproduce this this board using a standard breadboard like this. This is made by Chris Roper in South Africa, to who I'm very grateful. And we're just going to use the LEDs that are in here and a potentiometer, and we're going to make it dim. That's the basic way. So what we're going to be doing is having a signal. We're going to change it, create a square wave, and we're going to make the LED get brighter and dimmer. Okay, so we're going to actually do that. It's very simple. It's not too complicated at all. Let's just get into what is pulse width modulation. So it's simply a succession of pulses coming out from the microcontroller. Okay, that it just reduces the average power that's being delivered to an electrical device like an LED. So it chops it up into discrete parts at a specific frequency, which you can control, okay, for a particular duty. And that duty is, proportional to the power. And as you can see, I've got a square wave in the diagram increasing in width. Pulse width is increasing, and the average power on the device would go up or down proportionally. So, it is around controlling the on and off cycles at a very fast rate, and the longer the signal is on compared to the offs, it's total power supplied, and things get darker and brighter. And it's as simple as that. Now, what I've done, I have changed the setup. I have got my little XMega X Mini Lab scope hooked up. So we're going to see the actual scope, and I've got it connected into the ground, okay, the 0 volts, because it has to be, and then I've got it connected to the output of the potentiometer, which is I'll just get my pen up here. So this line here, which is port 1, is connected to the LED, and this is an LED signal, and it's going to be representing all the LEDs, okay? So this one, port 1, is connected to the LED, so we can see the square wave on the LED. And port 2 here is connected to the potentiometer, so we can see what the potentiometer is set to. And that's quite important because I want to replicate exactly this diagram. It's quite easily done. Erase that. So what we're going to do is look at the code, and then we're going to review the results. But I want to just show you it's actually working so that we understand the baseline, what we've got here, okay? So I'm just going to look in on the scope here. Now I've got software loaded on my computer, and that software is doing exactly what I've described. There is a square wave in the software, and I'm going to touch the PCB here on the potentiometer, and as I rotate it, the power, or the red line, goes down, and the square wave, the duty cycle, is reduced. Now, this is sampling at this is doing quite a bit of sampling here, my PC, but as you can see, as I increase the power on the voltage on the potentiometer, I get a square wave, okay? There we go. I think we'll have a little play with that little signal there. I think I've got a bit of a sampling issue on my scope, but it's showing you it's showing you that the LEDs are going brighter as the power is increasing, and that voltage is proportional. So that red line is proportional to the duty. So how do we do that? And if you look at the scope at the top, you can see that the scope here is actually the same as on the PC screen. So how do we do that? It's relatively simple. We've seen most of this code before, so I'm not going to spend too much on it. But essentially what we've got here is a chip line for the actual 18F. Shall I zoom in a bit closer? There we go. Chip line for the 18F, and then option explicit means I've got to define my variables. Okay. Now, let's just be very clear about what's going on here. Okay. I'm using a module called CCP. And that module, as yesterday, uses PPS. So we have to set up the PPS. So if I set up the PPS for this, I'm just going to type it into my computer here. I'm going to bring it up and show you that setup. So I'm going to set up the PPS for CCP PMW to those LED ports that we've been using in the past, which is RC0 to RC3. So let's look at my desktop. Here is the application. I'm going to this is the PPS tool 18FxxQ41, and I'm going to type it into the screen rather than just make it up. Okay, all right. Oh, here we go. I'm going to have to select it. There, 16FQ41. Now, can I zoom in on PPS tool for you? Yep, there we go. Great. So peripheral output. I want CCP1, because that's the one I'm going to be using, but look, there's only one in here. Some microcontrollers have 4, they have different numbers, so again, health warning, you can only use the PPS setup for a specific chip. So I'm going to add in that to RC0, add in RC1, so I'm going to make all 4 LEDs come on simultaneously by adding in and saying the pulse width modulation that I'm going to be enabling via CCP1 is going to come out on all 4 LEDs. I copy that into my cut and paste buffer, and then I can paste that back into here if I wanted to reconfigure it. So in here, it tells you each 2 lines, it says I have connected it, I've selected to connect the module of CCP1 to RC0, and these are the setup that are required. You can do this from the data sheet, but I wouldn't be bothered. Okay. Job 1: PPS setup. Documentation is set up. Inputs and output set up, all the same as previously. We've seen before how we're going to read the ADC, and I'm going to put it in a variable called ADC val. And I'm going to scale it. Why do I scale it? Because the actual voltage, I can prove it to you today, the actual voltage is less than 5 volts, and therefore I'm going to scale it back to, and I can show you that in a moment. Small delay, and then this is the killer line. It's very simple. Hardware, PWM, channel 1, because we've selected CCP1, a frequency of 10, arbitrary number, could be 40, depends what your motor, depends what you're connected to be quite frank. The frequency sometimes on a motor needs to be very specific, so select that number, and then I'm going to send it the ADC value, and that is representative to the duty cycle. So my range here of 0 to 255, I'm going to send it as a range of 0 to 255, and that is simply the setup. Let's program that. We'll see it flash out in the programmer. It's doing it now. And there we go. I have created a program. I'm going to change the frequency. If I halve the frequency, I'll double the frequency. I'll put a 2 in there. And we will see the oscilloscope change its frequency because I've doubled the frequency. We won't have 3 little on there. We'll have 2. Oh, that surprised me. You fool. That's the frequency. Press F5. Just programming it. And now, by halving the frequency on the screen, I'm getting only one square wave. So if I double the frequency, I should get twice as many. Meanwhile, I'm going to move over to here. I'm just going to try it. There we go. Perfect. And as I rotate it, the red line you can see is going up. The sampling there is a little bit strange, never mind. And it's full on, I get a full signal. And when I turn it down, I get no signal. So the pulse width modulation has gone to 0 because the duty cycle here, the value of ADC is now 0. And we could output that on the serial port if we wanted to see the values, okay? But if we want to see the actual voltages, I can select that over here. And here we go. I wonder if that's actually going to show us anything on my software. No. Let me just come out to the oscilloscope software. Oh, it's come up, great. But you can't see it on the screen, which is puzzling me. Scope. There we go. So as I rotate the potentiometer, the voltage increases. And so does the bottom number there of 3.8 is the maximum voltage that's on my channel 2, and that's because there is on this board here there is a resistor, a current limiting resistor that's effectively creating a voltage divider, which says the maximum is 3.82, and that's okay. And as you can see, as I rotate it, the voltage drops. In the program, recapping the program, what that is doing, it's reading it through on the ADC here, putting it in that value, in that ADC variable. I'm scaling it up just so that we can get it to go full on. And then I wait a few moments, 10 milliseconds, and then I'm saying, okay, hardware, PWM, channel 1, frequency, and then I'm sending it a value of 0 to 255, which is representative of the ADC. That's why I like this, because you really do get to see that light dimmer in operation. Pretty cool, yeah? Pretty cool stuff. Okay, using PMW with Great Cow BASIC is extremely simple. I wanted to show you this. The command is Pulse Width Modulation, PWM. Okay, job done. So today we covered using CCP. Tomorrow we're going to move into using I2C, I2C, I've been told, to discover some I2 devices, and then we're going to do some EEPROM memory stuff, and then we're going to go through some graphic stuff. So let's get progress. Let's enjoy this tutorial. We'll call that a wrap.